When people talk about climate change, often I hear the word global warming. I don't like that term because it does not fully cover and comprehensively describe what we are talking about. We are talking about changes in all components of the climate system that concern most physical variables and concern also other areas like ecosystems. It's an Earth-encompassing change at which we are looking now. But obviously, it started from observing the temperature, and that is where the origin of this term comes from. So let's look at the temperature first. We see that over the last 120 years, the Earth's mean surface temperature has increased by about 0.85 degrees Celsius. Now people tell me this is a very small amount. It's even less than 1 degree. But humans are kind of strange species when they talk about temperature, because in certain areas we have a very fine sensorium and feeling about temperature changes. Take, for example, if you take the temperature measurement of your baby. It actually depends whether you measure 36.9 degrees Celsius and everything is fine. If you measure 37.0 degrees Celsius, you have identified some developing fever. So only 1/10 of a degree in this temperature measurement is for us of concern. And it is similar in the Earth system. By looking at the global mean temperature, seeing that this temperature has risen already by 0.85 degrees, and also recognizing that with the increase of greenhouse gas concentrations, which today for carbon dioxide are 30% higher than ever in the past 800,000 years, we are heading towards a climate that has a much higher temperature in the near future if these emissions are not stopped and greenhouse gas concentrations are not stabilized. So let us take a more comprehensive look beyond the temperatures. On the long term, I've already talked about the composition of the atmosphere, which today is very different from the natural conditions that scientists have reconstructed thanks to the analysis in polar ice cores from Antarctica. We can reconstruct the greenhouse gas concentrations and note that today's concentrations are very different. This also concerns the water cycle. We already note that in the past 60 years, the global water cycle has changed in that wetter areas have become wetter and drier areas have faced some more dry conditions. We also see that sea level has risen by 19 centimeters, itself one of the most impressive changes in the climate system concerning one of the primary resource of humans, the access to land to build cities, land to live, but also land to produce food. And that means that this resource is threatened in the future as sea level is continuing. One of the most impressive observations of climate change, however, is the recognition that the whole world ocean has warmed up in the last 50 years. Temperature measurements that cover essentially the entire ocean surface and also the ocean depth down to 2 kilometers allow us to estimate the amount of energy that has penetrated the ocean over the past 50 years. It's a staggering amount of 250 times 10 to the 21 joules. An amount of energy that is almost unimaginable, but it is in front of our eyes thanks to very precise temperature measurements of the scientific community around the world. This is an impressive manifestation that man has changed the face of the Earth. We are, through the emissions of greenhouse gases caused by the burning of fossil fuels and deforestation, changing the fate of this planet. When we talk about the warming, I often hear people talking about the past 15 years. Some even talk about a warming pause. Here I think it's very important to look at the facts like the scientists do. They look at the measurements and they ask questions. Do we understand this short-term variability of the global mean temperature that shows sometimes a large trend, sometimes a lesser trend if you look at 10 years or 15 years. What we have noted is that since 1998, if you start to calculate 15 years trend, that trend is a bit smaller than the longer term trend over 60 years. But it very much depends at which year you start your analysis. If you do that from 1998, you get about 0.05 degrees Celsius per decade as a warming trend. Had you started 2 years earlier in 1996, your calculation would yield 0.14 degrees Celsius per decade, which is almost 3 times larger, which is a very clear indicator that looking at 15-year trends only does not tell you much about the long-term climate change. And that is why the scientists focus on very long timescales, many decades, more than 100 years, using paleoclimate data. They even go back for 1,000 years and try to compare the climate of today with the climate over the last 1,000 years, with some very interesting and important insights regarding the natural variations that nature is able to create, superimposed on the long-term trend that is caused by human activity. In addition to the temperature changes that are probably the easiest to measure, scientists now also can affirm large changes in the frozen world, the cryosphere. The mass of the ice sheets in Greenland and in Antarctica is shrinking at an accelerating pace. We're losing ice because of the warming in the high latitudes. Ice is melting and contributes substantially to sea level rise. We also note that the Arctic ice cover has shrunk not only in extent during summertime, but also in thickness, which means a totally different quality of the ice that we are now encountering in the Arctic, a quality of ice that is much more vulnerable to high temperatures than much thicker ice that is able to buffer the changes. One of the changes that almost goes unnoticed by the public is the acidification of the ocean. With the increase of carbon dioxide in the atmosphere, the ocean becomes more acid, which means that marine organisms that create shells that need to calcify, extract calcium carbonate from the water, they get a much harder time to build their shells in an environment that is more acid. This acidification is one of the largest scale impacts with the longest time scale that man is inflicting on this climate system. We know that once carbon dioxide is emitted and creates the warming in the atmosphere, but also the acidification in the ocean, this carbon dioxide stays in the atmosphere for many millennia, which means that the changes that we are bringing into the climate system today will be with us for a long, long time. Like in any scientific endeavor, there are still many open questions. They don't fundamentally put into question our knowledge on climate change, but they concern important issues that we would like to know better and better understand. I can think of 3 issues here. The first concerns the water cycle. As water is the primary resource to humans and ecosystems, we would like to know how the water cycle responds to a warmer world. Where are the areas that receive more water? What is the change in seasonality, for example, in precipitation? These are important questions when it comes to trying to evaluate and estimate how ecosystems, forests, vegetation, eventually food production will respond to climate change and what options there are for adaptation. The second concerns the question of instabilities in the climate system. Observations indicate that some of the large ice streams may become unstable in the near future. Some already show some signs of instability in Antarctica, which has serious implications for sea level rise. However, the physical mechanisms and the observational database are still limited, and I hope that in the future that the scientists together with theoreticians understanding these processes would be able to better inform us about instabilities and the proximity to which we will come in the near future. And the third point concerns the ocean. The ocean as a vast reservoir of heat, but also carbon dioxide, acidifies. And that effect on marine ecosystems and marine life, one of the future food stores of humanity, is very little known. We don't know what the response of these ecosystems will be to an ocean that will be more acidic and warmer, that also has a change in sea level, questions that need to be urgently addressed by a concerted effort of interdisciplinary action by physical scientists, biologists and chemists.
So in studying the climate, we can do it in many different ways. We need observations to tell us about the structure of the atmosphere and oceans and how they change. And then we need the physics to understand that. And then we now increasingly use climate models. And by that, I don't mean a physical model constructed out of string or straws or plastic or whatever. I mean a computer model, which is based on the fundamental physics and mathematics that we understand and put into a way that the computer can interpret and integrate. So climate models are, as I say, built on very, very basic physics understanding. So if I can just go through some equations that you may be familiar with. The first one is Newton's second law of motion. You will know force is mass times acceleration, or acceleration is force per unit mass. So now we're talking about the forces acting on a parcel of air, or indeed in the oceans, but I'm going to focus on the atmosphere. And the forces acting on a parcel of air are, number one, gravity. We'll be pulling it towards the Earth. Number two, pressure gradients. So you have seen weather maps with high pressure regions and low pressure regions. Everything else being equal, the air would try to go from the high pressure to the low pressure. It doesn't because of the next sort of force. It's not really a force, but it's how it appears to be a force. It's called the Coriolis force, and that's due to the fact that the Earth is rotating. And the fourth force we need to consider is frictional drag, or viscosity. So we can write down force is mass times acceleration with those forces, and that's the first equation, or actually three equations because it's a vector. We've got to go up, down, left, right, and forward and back. So there's three equations there as a starting point. The next equation that we use is conservation of energy, and that's telling us that if we have a parcel of air and we add heat to it, either it will get hot or it will expand. That's a very easy to understand equation. The third equation is conservation of mass, and that's saying that if we have a volume of air and we have motion through it, if the air accumulates, the density will go up or it'll go out the other side. So that's just conservation of mass. And the final equation is just the equation of state. So you will have heard of the ideal gas law, for example, PV is RT, or there's other equations of state. That's the most simple one. So now we've had 6 equations, 3 for the momentum, 1 for the mass, 1 for the heating, and 1 for the equation of state. 6 equations, and we've got 6 unknowns. We've got pressure, temperature, density, and 3 components of wind. So we have simultaneous equations, and we can solve them. So I described the fundamental physics that goes into the equations that are used in the climate models, but of course the problem comes in the implementation. So in the thermodynamic equation, I mentioned how we needed to know the heating sources, and they will come from, for example, solar radiation heating the atmosphere, heat radiation leaving the atmosphere. They come from latent heat release when water is evaporates or condensed, and all those need to be included in this heating term. Then I described how we need to know about the frictional forces, and here of course we need to have some sort of representation of air flowing over rough surfaces, so forests or mountains, and again this is very difficult to prescribe accurately. Another factor that we need to include in the models is the topography. So we can either have a very smooth surface, or we can try and put in the mountains and cover properly. And indeed in the climate models they will have topographic variations, mountains and valleys prescribed at the resolution of the model to try and make it more accurate. So that brings us on to the whole issue of resolution. When we write down these equations, we can do them in a variety of ways, but the most common way is to write them each on a grid which is covering the globe, perhaps latitude and longitude, and then different levels in height. So you've got a three-dimensional grid, and you solve the equations at each of these points on the grid. You iterate in time, and you solve them all again, and that is what is running the computer model. Another complication that I haven't mentioned yet is how we create clouds and indeed rainfall and snow. So we understand the physics of clouds to a fairly good extent. It's been studied over many years, many centuries indeed. So when you have air rising, it cools and the water vapour tends to condense out and form clouds. So while the fundamental equations are very easy to write down and very easy to understand indeed, actually the implementation becomes more complicated, and the actual physics, the gut physics of the problem needs to be specified very carefully. And then we integrate in time, and we can understand actually the same equations are used for forecasting the weather as for integrating into climate into the future. So we step forward in time and we see what happens. Now, when you set down these equations on a grid and you're going to solve them numerically, you have to start from somewhere. If you're doing a weather forecast, you have all the data that's coming in today, and you start today and you do it tomorrow, and then you correct it from the data and you do it again, and you correct it again and you do it again. And each time you're essentially initializing the whole data set. You're sort of making sure that it's starting in a correct place. What we find with climate modelling, very long distance into the future, is that if we start from a very slightly different initial data set, the evolution of the climate will go in different ways. So you can start it from a slightly different point, and it will wiggle into the future in different sort of ways. And you can run this hundreds of times, and you'll get different wiggles overlying each other into the future. So we can't say particularly what wiggle it's on. The Earth will be on one wiggle, but we can't say precisely which wiggle. But we do know that averaged over all of the wiggles will give us an envelope of possibilities into the future. And indeed, when we forecast climate change, we can see how we get an envelope of variability which tracks into the future in one way or another, depending on what we assume, particularly with regard to the concentrations of greenhouse gases. When we use climate models, we need to think in advance what question it is we're trying to answer, or what it is that we're actually trying to use them for. So we have this big climate model, and we can ask different questions of it. We can say, what would happen if the cloud physics is slightly different to what we had originally assumed? That means, for example, if the air temperature went a little bit colder, and would the ice crystals get a little bit bigger? How much would that affect the temperature? How much the temperature would affect that? And how much that would affect the climate in general? That's one particular question. Another question is how we represent air-sea interactions. So I've talked about heating of the atmosphere. There's also heating of the oceans, and there's transfer of heat between the atmosphere and oceans, and indeed, of course, of water vapour, and how we represent those processes and how they depend on the wind speed and on the humidity is all crucial to how the model behaves and how we understand the behaviour. If we want to look into the future, looking ahead to what is going to happen with climate change, of course we have to make some assumptions about how the composition of the atmosphere will change, and that's a big question that climate scientists can't answer. That's really for the economists to tell us how much coal or whatever is going to be burnt in the future, what will the CO2 concentration of the atmosphere be, and then we can use those as input data to the model and see how they respond. We can also look at the coupling between things like climate change and temperature and air quality. So you'll be aware that when you use coal-fired power stations, they not only emit CO2, they also emit an awful lot of particulates. Basically, it's sulfate particles. And so those sulfate particles will affect people's health, but that's not what I'm going to talk about now. It'll also affect the radiation balance. It reflects sunshine back to space. So there's an interesting byplay between the greenhouse gas heating the atmosphere and these particulates reflecting sunshine to space, which tends to cool the atmosphere, and how these two things interact together. And that depends very much on the physical properties of those aerosol particles. So again, we need to prescribe these in the model to try and see if we can get a better simulation. So there's a number of developments in climate modelling, all of which are very interesting and very exciting. One, of course, is the use of more and more high-powered computers, which is going to enable us to have much better high-resolution simulation, so higher spatial resolution, but also better representation of individual processes. So we're never going to be able to simulate in detail all the parts of the climate system. You'd need to get down to tiny little scales of molecules. You can't do that. But if we can get down to, say, 10 metres, then we can really see the shape of clouds, for example, which we can't do at the moment. There's also better understanding going on of the physical processes, indeed these processes between the particulates in the atmosphere. So we've got industrial pollution, we've also got natural particulates, say sea salt, we've got dust coming from the blown up from the deserts, and all these things hanging around in the air, and what they do to the radiation budget and the climate. We'll be able to understand that in more detail in the future. Tying all these things in together, I hope and I predict that we will have a much stronger ability to constrain how climate is evolving and our understanding of it into the future.
In the middle of the 19th century, a man called Louis Agassiz was looking at the geology in the Alps and concluding that the valleys that he'd been seeing and looking at, and a lot of the landforms that were around in the Alps were evidence of the whole valley being occupied by ice. The landscape was formed by the action of ice. Now at the time that was quite a strange thing to say, because the general idea was the landscape had been given to us by God. And so what he was saying was that that wasn't necessarily true, and that physical processes were responsible for that action. And he toured around Europe, telling people what he'd found, convincing them one by one. Even Charles Darwin was a convert to his theory. He first thought that the landscape was indeed given to us by God, but he changed his mind after seeing the evidence. The evidence of former glaciers in Europe and in North America is evident for everybody to see. You don't need to go very far to see mounting valleys formed by the action of ice where there no longer is any ice. And glacial theory was established as an idea, the idea that the world once had a lot more ice in it, an ice age. Well, this idea by the end of the 19th century was pretty well accepted, and that the Earth had experienced an ice age in the past. And what we wanted to understand was what caused the ice age. And so by the end of the 19th century, people were starting to put some ideas together. And one person who put an idea together was James Kroll. And he was a self-taught mathematician, worked as a janitor in a museum in Glasgow in Scotland. And he came up with an idea to do with the Earth's orbit around the sun. The Earth orbits around the sun, of course, but it doesn't do it in a circular orbit. It has an elliptical orbit, and that elliptical orbit changes through time. And when we're closer to the sun, we get more sunshine and more sunlight and more heat. And when we're further away, we get less. And he worked out that if we get less heat at certain times of that orbit, then it could be that the amount of solar radiation coming into the planet is so small that it can cause the ice masses to expand. That was his idea. And people thought that was a pretty good idea. But unfortunately, by the time he died, no one believed that idea at all. And so he died sort of unfulfilled and people not believing his big theory. A Serbian mathematician, Milután Milanković, in the middle of the 20th century, picked up the idea and added some refinements to it. And again, everyone thought this is a pretty good idea and it explains glacial theory and all to do with the way the Earth orbits around the sun, the amount of sunlight that we would get from the sun as a consequence of those orbits. Unfortunately, he died with no one believing his theory either. It took to the late 1960s and the ice core at Vostok Station to make both theories that had come previously accepted. And it's this: the ice in Antarctica is a time machine. Snow falls on the surface of the Antarctic. That's all fine, and people understand that. And when you have a snowball, it's pretty light. It's got a lot of air in it. Now, in the middle of Antarctica, at the very middle, where Vostok Station is, there's very little sideways flow of ice. Most of the flow is downwards due to the burial of snow by subsequent snowfall. And so as that snow gets buried deeper and deeper into the ice, at a certain stage, about 70 years after it was once deposited as snow, the air within the snow gets cut off from the atmosphere above. That snow turns into ice, but the air in it retains as bubbles within the ice, and it gets deeper and deeper and deeper. The ice beneath Vostok Station is 3,700 meters thick, and the ice at the bottom of that was deposited 450,000 years ago. So if you have an ice core and you drill down all the way to the bottom of the ice, Vostok Station, you pull it back up and you sample the air within it, you're actually sampling the actual air that existed all that time ago and every year in between. We have a continuous, direct measurement of the Earth's atmosphere and its constituents, the composition, for the last 450,000 years. It's a remarkable thing. And when you look at the way that the Earth's atmosphere changes, and there are various ways we can reconstruct temperature from that, you see the types of change is exactly what James Kroll and Milután Milanković have proposed. I mean, it's too much to be a coincidence. So all of a sudden, the idea of orbital variations around the Earth causing ice ages was accepted again. But the reason that Milanković and Kroll weren't believed is because the changes that they were proposing, the solar changes they were proposing, are very, very small, a few percent in terms of heat coming in from the sun. And people were saying that can't possibly cause ice ages. And it's true, that's not enough to cause an ice age. But what they weren't appreciating, those early researchers, was that the Earth doesn't work as a series of feedback processes. And what the Vostok ice core demonstrated was that it was carbon dioxide was the big driver of the change. The carbon dioxide level recorded in the Vostok ice core goes from about 180 parts per mil during ice ages to 280 parts per mil. That's within ice ages. And 200 years ago, that's what the level of carbon dioxide in the atmosphere was on Earth right now, and that's what it should be, 280. And so carbon dioxide is a big driver. Where it's low, you have less greenhouse gas, colder temperatures, ice ages. And when it's high, 280, warmer temperatures, interglacial conditions. Ice ages are paced by the orbital variations around the sun, but they're driven by the carbon dioxide content. And so that's what we've learned from the Vostok ice core, and that's what we've learned about ice ages. Now, where are we now with carbon dioxide levels? Since 1850, we've been burning fossil fuels at an industrial rate to fuel industrialization and mechanical processes and the way that we transport ourselves around the world. Carbon dioxide levels now stand at 403.5 parts per mil. That's over 100 more than they should be. The last time we had that level of carbon dioxide in the atmosphere was in a period in time called the Pliocene, 3.5 million years ago. Sea levels were 15 to 20 meters higher, and the global temperatures were 3 or 4 degrees higher than they are right now. This is why we have to worry about carbon dioxide in the atmosphere and global warming, because if we do nothing about it, that's where we're headed. We're headed to global temperatures 3 or 4 degrees higher than they are now, and sea levels over 10 meters higher than they are now. Might take a while to get there, but that's the destination. So when you extract an ice core, it's like 3 kilometers long. You do it in bits, of course. And those bits of ice core are taken into a laboratory, and they are sliced into very thin layers. And those bits of ice are then looked at for their chemical composition. You know, what is in the ice? Apart from water, what else is in the ice? And there will be air bubbles within that ice, and those air bubbles can be sampled. There'll be dust in the ice, and that dust can be measured. Everything can be measured. These are very valuable samples, and it costs a lot of money to get an ice core. And so we do a very thorough investigation on every single little bit of the ice that we extract. And what it tells us is important information about the atmosphere and what it was during the time that that ice was once snow falling on the surface of the Antarctic ice sheet. It tells us about the dust that was in there. It tells us about methane that's in the atmosphere. It tells us about carbon dioxide. It tells us about the isotopes of oxygen. Everything that we would want to understand about how Earth's climate has changed in the past is encapsulated within a little bit of ice buried beneath the surface of Antarctica. So ice cores tell us about the long-term history of climate, from ice ages to between ice ages, and that's really good. But they also tell us about more short-term variations as well. And in particular, the ice cores in Greenland. Greenland is also a very big ice sheet, and it's 3 or 4 kilometers thick in places. What the Greenland ice cores tell us is that at some times in the last 20 to 10,000 years ago, Earth's climate changed by plus or minus 5 degrees centigrade over a course of just a few decades. And the reason for that is because water coming off the melting ice sheets in North America during deglaciation was interrupting the heat transfer in the North Atlantic, the thermohaline circulation. The world's oceans flow in an interconnected way, driven by salinity, salt changes in the North Atlantic. And if you put fresh water into the North Atlantic, you stop that flow of heat. And if you stop the flow of heat, then Great Britain, other parts of Northwest Europe suddenly become much, much colder. And so that's what the ice cores in Greenland have demonstrated. The Earth's temperature around Northwest Europe changed from plus or minus 5 degrees centigrade over just a few decades. It tells us that when you melt the ice, if that meltwater goes into the North Atlantic, we can change the local climate significantly. So the big questions in the study of ice and in glaciology is how the ice is going to change with climate change, and what those interacting processes are going to be as well. I mean, it seems quite a straightforward question. You have a block of ice on land, and the Earth's surface warms, the air warms, and the ice melts, and it goes into the ocean, and the sea level goes up. And it's pretty straightforward, right, if you think about it in those ways. But actually, what we have is an interconnected series of different processes which are going on. We have, for example, the oceans, and the heat transferred around the oceans is remarkable. We get about a third of the heat that we get from the sun in the United Kingdom received from the ocean as well. The oceans are massive stores of heat on our planet. And if the oceans change, then the heat supply around the planet will change as well. And so this is something that is driving us. As glaciologists, we're not just interested in the ice, we're also interested in the oceans as well. And the ice ocean interface is sometimes the most difficult bits of an ice sheet to get to. And that's where the interesting questions are right now. So it's undeniable that glaciers are retreating. All the glaciers around the world are largely retreating. And it's undeniable that the ice in Antarctica and Greenland is experiencing some loss as well. And so sea level is going to go up. And it's likely sea level will go up by 0.5 meter in this century, irrespective of what we do. The challenge for society is to stop the level of sea rise going up by more than that. And if we don't tackle climate change, if we don't stop greenhouse gas emissions, and the world's temperature warms by 3 or 4 degrees centigrade, then we won't just get 1 meter of sea level rise, we'll get much more than that. And it won't just be finishing this century, it will be going on for the next several centuries as well. So what we're looking at here, people around living on this planet right now, we have a big choice to make. We can do nothing, and then our future generations will have to deal with the consequences of that in terms of a warmer world and one with sea level much higher. Or we can do something, and we can change our ways, we can reduce greenhouse gas emissions, and we can stop the effects of climate change from being as severe as they might. Now, we can't change them all. It's already too late for some things. Sea level is going up. 0.5 meter by the end of the century is extremely likely. But we can stop it being worse than that. We're the first generation to know that climate change is happening, that people are responsible for climate change, and that we can do something about it. No other generation before us had that 3 bits of information. It's just us. If we don't do something about it, in history, we won't look so good. This is our greatest challenge, and we have all the skills available to do something about it. We've got all the predictions available to tell us why we need to do something about it, but it's up to us to do it.
So at the moment, perhaps the main environmental concern for freshwaters is coming from climate change. And climate change is not just global warming, it's also changes in precipitation in different regions. So for example, as climates get warmer into the future, this will cause, for example, the Asian monsoon to change when it falls most in different countries. And so in terms of freshwater security, this is going to also cause problems for potentially billions of people. Climate change is just the latest kind of threat to freshwaters. So I would say that in the 1980s, it was to do with freshwater acidification and acid rain. In the 1990s, it was really to do with nutrient enrichment from agriculture. And then in the sort of 1990s going into 2000, when we realized that global warming was perhaps the temperature the highest they've been maybe for the last 1,000 years, then global warming became kind of sort of the major environmental concern. So climate change can affect freshwater in many ways. So in some of my own research that I work on, for example, in Lake Baikal and in other lakes in Russia and in southern Siberia, here the lakes freeze over every year. And that freezing over every year means that the lakes contain species that are really uniquely adapted to those kind of situations. If you imagine that as global warming gets warmer in the future, then the ice cover on those lakes is going to be there for a shorter period of time, and the ice will become thinner. So for many species that might be problematic. So for example, we have on Lake Baikal, we've got the world's only freshwater seal. It's uniquely tied to the ice in the lake. And the ice starts to disappear, then the ecology of that species is going to change as well, and that will have a cascading effect elsewhere. And we know from many studies around the world now that ice cover, the thickness of ice, the duration of ice in lakes is getting shorter with every decade that passes. So that's going to cause major changes to the ecosystems. We don't really know what's going to happen. We can predict what's going to happen. Global warming also causes lakes themselves to warm up during the summertime, for example. And that can be problematic because when lake water becomes warmer, that warmer water becomes lighter and it sits on top of the lake. And that means that some species like these one-celled algae called diatoms or the glass shell, they become too heavy and they sink out of the light zone and they start to die off. And in their place, we have these smaller algae. And these smaller algae can form dangerous algal blooms, such as cyanobacteria. And we have an algal bloom. That means that the algae bloom, but when the algae die, they start to respire more and they use up all the oxygen, and that can cause dead zones, again, in lakes. And if you've got no oxygen, you've got a dead zone, then that means that fish can no longer live there as well. And so we're seeing in many lakes now that global warming is causing these dead zones to become more common, and that can be problematic. And from a recent survey done of lakes from around the world, the majority of them are heating up in the summertime. And again, we don't really know what's going to happen with them all. The responses will be different depending on where in the world that you are. If you go to tropical lakes, for example, they're already very warm. And so if you imagine that global warming is going to warm these lakes even further, some of the species there are uniquely adapted to growing in these warm waters. If it gets even warmer, that may be at the physiological tolerance of some species, and then those species might start to die out. And what we're seeing in some of the tropical lakes in East Africa, these large, deep tectonic lakes, is that already we're seeing some loss of species, and we're seeing some loss of productivity in those lakes that is linked directly to global warming. Some lakes that exist in regions that are semi-arid, so they're reliant on sort of precipitation, evaporation, etc., sort of in desert regions, basically. If we're going to have changes in rainfall, and say we have less rainfall, then those lakes are going to start to dry up. And if they start to dry up, that means they become more salty. And if they become more salty, then they become too salty for organisms to live there. And then those organisms start to die out. And that's exactly like the RLC that we saw there. All the fish died out because the lake shrunk to such an amount, it became too salty. And then becomes too salty, it's a problem that humans can't drink it either. So we have these different things that climate change is going to affect lakes in the future in different parts in the world, and that can be problematic. It can get worse. So we know that, for example, nutrients cause a problem for lakes and that they cause algal blooms. When a lake warms up, that can also cause algal blooms. So if you've got nutrients coming into the lake from agriculture and you've got the lakes are warm at the same time, we have these interacting stressors that can actually make the situation even worse. And so in many lakes we're seeing, for example, in South America, Lake Valencia, we're seeing the effects of this, whereby we've got these massive algal blooms, we've got these really rapidly increasing dead zones, and then sort of death of fish and other organisms. And there's been a really, I'm saying a nice case study, but it's not a nice case study, it's a novel case study. And this is Lake Pupo in South America. It's very sensitive to changes in evaporation, but also in the lake's catchment, there's lots of mining going on there. And because lots of mining, that mining is producing lots of toxic heavy metals that's getting into the lake via the rivers. So the lake is becoming really stressed. And there's been well-documented changes in lake water quality, which is problematic for the people that rely on the lake, but also is causing species to become threatened, and they're starting to die off as well. And then in about sort of late 2014, 2015, there's a major extreme event in the climate linked to El Nino. And that caused the lake to heat up a lot, and I mean a lot. And that caused the lake to have these algal blooms, which meant that the oxygen was lost. And because of the unique condition at the time, the wind blew the water that had no oxygen into the coastline where all the fish were living. And that meant millions of fish died out as well. So here we have an interaction of climate and human activity that are interacting together that's causing conditions to become even worse. And with global warming, we're seeing temperatures sort of increase gradually. But what the big unknown is are these extreme events. So these big El Nino events that happened just 2 years ago, where we have these like very extreme either precipitation happening or very extreme increases in temperature. And that is a great unknown. That is going to really disrupt the ecology in these lakes. And I think that is some of the work, a lot of the work is going on at the moment. But yeah, that is probably the scary thing that's happening, I think, in lakes at the moment. I think people can adapt to changes in around lakes and in rivers if the change is gradual. So lakes are heating up, but they'll heat up over decades. And I think they'll just have to adapt their economies because they can't control global warming. It's when you have an extreme event, say you have massive flood, for example, so where we have an increase in hurricane intensity or an increase in typhoon intensity in Southeast Asia, when that brings vast amounts of water coming in, that water hits the mountains, hits the catchment, rivers burst their banks, they bring in lots and lots of soils, contaminants, etc. into the lake that you can't prepare for. Or it's less easy to prepare for that, I think. And so I think a lot of the work that's going on at the moment is in looking at adaptation to these extreme events. Looking at disaster resilience as well, to try to work out, well, if we do have an increase in intensity of hurricanes or typhoons or monsoons, how can we adapt to that? How can populations adapt to that? Lake levels might be increasing. That means that you don't build beside a lake. You don't build on a river floodplain if you think that you're going to have more flash floods that are going to come from global warming. Because of course, as the atmosphere warms up, it can hold more moisture. But then that moisture's got to go somewhere, and that's why we're seeing, even in southern England, these major rainstorms that happen that cause flooding. So I think there are local adaptations that people can make. Don't build in floodplains. Those are some of the things that are key. But of course, that takes a lot of will. It takes a lot of governments to make decisions that will have an impact on policy decades in advance, and governments can be slow to do that, I think, which I think is a bit unfortunate. So I'm mainly going to focus on freshwater security that comes from surface waters, from lakes and rivers, and I won't touch on groundwater because that has its own implications and problems in different parts of the world. Freshwater security is important in terms of, for example, what we call ecosystem services. So an ecosystem is where you have a group of microorganisms, plants, animals that live together in, for example, a water body, and they interact together with the chemistry and the climate, and that's the ecosystem. An ecosystem service is the benefit that ecosystem provides humanity for well-being. So for example, with lakes, they'll provide benefits in terms of fish for protein, for food, economy. They'll provide water, for fresh water for drinking. Lakes also help to clean up water, they help regulate the carbon cycle, they help regulate climate change, etc. If we start to disrupt the ecosystem functioning of lakes and rivers, then we also pose major threats for freshwater security. So an excellent example of that is the RLC, for example. So the RLC was once the 4th largest lake in the world. It exists in the former Soviet Union between Kazakhstan and Uzbekistan. But then in the 1950s, the governments there thought that they would want to promote further cotton irrigation in the catchment of the RLC. Now the RLC exists and is it exists in the middle of the desert. So it's very sensitive to changes in precipitation. It's very sensitive to change evaporation and the rivers flowing into it especially. And so the 1950s and 1960s especially, water was diverted from the RLC for the cotton irrigation. And that meant that less water is flowing into the RLC itself because it's all going into the cotton plantations. So between 1960 and about 1980, the RLC lost about 90% of its volume. So it shrunk to a really small size. And that meant that all the hundreds of species that lived there all died out. the RLC shrunk to such an extent that it caused major health problems with local populations because they lost the fishing industry, basically. So the freshwater security that they had from the fishing industry, which is one of the biggest in the former Soviet Union, just disappeared within a matter of decades. This caused their health become compromised, which meant that they were much more susceptible to disease. And so again, we can see that's kind of a very extreme example of how human impact on lakes can really affect freshwater security. So the World Economic Forum have recognized that freshwater security is one of the most important concerns going into the future because of population increases around the world. We are making more demands on fresh water for both drinking, but also industry and factories, etc. But one of the problems is that fresh water itself is very unevenly distributed. So in North America, it has over half the world's fresh water, whereas Southeast Asia has only about sort of 10% of permanent surface fresh water. But 60% of the world's population live in Southeast Asia. So the demands there are very large and very extreme, and that's why it is of a great concern. So there's been some very nice studies done that have looked at freshwaters around the world, and it's estimated that at about any 1 month of the year, about 4 billion people are exposed to threatened freshwater security. And that's defined by, say, people taking water out of a river that's more than is actually flowing through the river. And about 500 million people on the planet are exposed to very dangerous levels of freshwater security throughout the year. So we can see how it's an extremely important problem. Climate change is having some impact on that as well. Unusually, you might think that there's actually more fresh water in the world today than there was 30 years ago. As the volume is actually increasing, but is increasing in certain regions of the world which perhaps aren't needing it so much. And so again, that has kind of implications. One of the major things we're seeing with freshwater security now and into the future is linked to biodiversity. So freshwater covers about 3% of the surface of the land surface of the planet. Yet freshwaters contain 6% of the world's biodiversity. They contain over a third of the world's vertebrates and over 40% of the world's fishes. So that means for actually a very small amount of area, they contain a very high proportion of biodiversity. And that makes freshwater security and biodiversity very, very important. There's been this really nice study done called the Living Planet Index that's done by the WWF, the World Wildlife Fund, and also the Zoological Society of London. And they've looked at tens of thousands of populations of thousands of species from 1970 up to the present day. And they use 1970 as a baseline. And what they found for freshwater vertebrates is that they've declined in population by over 83%. So 4/5 of the world's freshwater vertebrates have disappeared. These are the wild vertebrates. And if you think that we rely on these vertebrates for food, for recreation, for ecosystem health, that is really, really damaging. And so I think in terms of, things like pollution of lakes can damage freshwater security, but we can clean that up. We can clean that up through international legislation, for example, for acid rain. We can clean it up through local and regional legislation, for example, through farming impacts on lakes and rivers. But when we look to biodiversity, it's very hard to regain those populations. And if populations keep getting less and less, that means that they could go into extinction. And then when you lose a species to extinction, you're never going to get it back. And so there's been a lot of talk about whether the Earth in general is moving into a 6th mass extinction. We're going to be losing all these species. And in terms of population decline, and especially in fresh waters, that is not negating that hypothesis of the sixth mass extinction. So we could be moving towards this kind of like this sort of tipping point in the Earth, and that in a sense is why freshwater security is extremely important, not just for human health and well-being in terms of fresh water. It's important for biodiversity in general around the planet. Biodiversity is important for regulating carbon cycle, nitrogen cycle. So again, all these things in the planet are all interrelated and interconnected. And if you start damaging one to such an extent, then that will have impacts elsewhere in the world as well. So in the last 10 years, a lot of the research has been using, for example, remote sensing from satellites just to actually characterize where is the water and where is it disappearing from, and potentially where to. So some studies that have come out in the last couple of years have shown that there is a lot of freshwater decline, both from, for example, from the Greenland ice sheet, the Antarctic ice sheet, and that's linked to global warming and that ice melting into the oceans. But also a large amount of decline from, for example, Northeast Asia, some parts of Central America, southwestern United States. And this seems to be from agriculture. And you've got such intense agriculture there that you're using up all the fresh water that you can see changes in the gravity of the Earth from that. And that is, that is some of the sort of cutting edge research that's showing areas of real concern in the last couple of years.
If you read a lot of papers, scientific papers on the subject, you would get the impression that the rapid climate change that is evidently starting now is something completely unprecedented. It's not true. Those of us who are interested in past climate changes realize that rapid climate changes have happened before. They're certainly not the same, certainly not with the same cause as what we see now. But they did actually happen. In particular, they happened during and at the end of ice ages. During the last 2 or 3 million years, the Earth has actually more often been in an ice age than in the kind of warm period that we're in now. In fact, about 80 or 90% of the time during that period, the Earth has been in an ice age. But during those ice ages, there were some strange things happened called Danskar-Oeschger events, or DO cycles. What happened was at some point, and this happened repeatedly during each ice age. So during the last ice age, there were about 20 such events. What happened was a rapid warming followed by a gradual cooling. The rapid warming took place in between about 50 and 200 years. The cooling was more slow than that. And the magnitude of the warming was rather large. It was spatially variable, being largest in the high latitudes, but in Greenland, for example, we know from ice core records that these warmings were of an amplitude up to 16 degrees. Now, that's a very big warming. In lower latitudes, something more like 5 degrees, but nevertheless very substantial warming in a rather short period of time. So what's happening today, simply in terms of the magnitude and speed of the warming, is not unprecedented. Because such things happen repeatedly during the ice ages, obviously then the living species must be adapted to some degree to deal with rapid warming. Perhaps the most remarkable example are the warmings that happened at the very end of each ice age. So it was like there was a final warming event which turned out to be the big one that pushed the Earth system into the warm interglacial period, the interglacial condition. And we know a great deal in excruciating detail about what happened more or less year by year 11,700 years ago, which was when the final phase of the last ice age, called the Younger Dryas period, came to an end. During that transition, there was a global warming by somewhere between 5 and 7 degrees, and it took place in less than 20 years. Now, again, if you read the literature about present species distribution and climate change, you might get the impression that we were about to suffer mass extinctions of large numbers of species on the grounds that they can't keep up with rapid climate change. Well, we do know during that transition period, at the end of the Ice Age, there certainly were extinctions. They didn't happen immediately, but certainly in a rather limited period around that time. There were large mammals in particular, such as the woolly mammoth, and which of course was very abundant in the high latitudes during the Ice Age, became extinct. The woolly rhinoceros and the giant Irish elk, and so there was a whole long list of large mammals that went extinct. Now, there's still a raging controversy about the role of hunting by Paleolithic people. To what extent were these animals forced to extinction by overhunting, or to what extent by climate change? And I despair of this ever being resolved. However, I think it's pretty clear that both were involved. It's hard to imagine this happening without climate change. Certainly they may have been given a bit of a push by human activities. But we do know, if we go back to earlier ice ages, we find there were also species that went extinct at the end of earlier ice ages as well, even without this kind of help from people. So climate change had a huge impact on mammals. What about plants? Well, we know quite a lot about the plants because we have a lot of fossil records, not only pollen records from all over the world, but also plant macrofossils. So we know about tens of thousands of species that were present in the Ice Age. We know a lot about them. So people are often surprised when I tell them how many species we know about that went extinct, how many plant species that went extinct at the end of the last Ice Age. So the total is 1. There is a species of spruce called Picea critchfeldii. It has been named and properly described as on the basis of fossil specimens that apparently went extinct. Plants apparently were very well able to cope. This has been called the Quaternary conundrum. The Quaternary is a name for the epoch consisting of the last 2 million years or so. How can it be that plants in particular were so well able to survive these extraordinary changes in climate that happened quite naturally? And it's obviously a question that has considerable contemporary relevance, because it suggests that predictions of widespread extinctions of plant species, or indeed many other groups that survived very well, such as most groups of insects, for example, even small mammals, did not suffer major extinctions. But the question is, how is it that they were able to deal with such rapid climate change, and what are the implications for the present day? It rather suggests that these dire predictions of mass extinction purely due to climate change can't possibly be correct. In a paper we published in Science a few years back, we analysed different types of behaviour that we see in the paleoecological record. So from fossil records we can infer that plants and animals had several different ways of dealing with climate change. There are some species that basically just stayed where they were and just put up with it. This is what we call tolerance. We have examples of each of these types of behaviour in the plant and animal kingdom. So tolerance is a simple behaviour. We have habitat shifts. So there are known examples where species didn't really move its range very much, but it did move the microhabitat that it occupied. So species of plant, for example, that tend to be found in a certain region on north-facing slopes. Now we're found on south-facing slopes, and so just nipped around the other side of the mountain. This is, of course, easier to do in regions of complex topography, but that's probably why mountain regions tend to be particularly species rich, is that species have been able to pull this kind of trick in the past when faced with climate change. So we have toleration, we have habitat shift, we have migration, and there are many, many examples where species of both plants and animals have actually moved their range by thousands of kilometers. And so they're evidently capable of doing it, even though climates have been changing rapidly. It's a bit of a mystery how they manage it. And finally, of course, there is extinction, and there are examples of extinction, but as I said, for plants, we have only one example. For large mammals, we have many others. Now, I just want to say a little about how this issue has been treated in recent assessments, because I think there is a major issue that requires resolution. Every 6 or 7 years, the Intergovernmental Panel on Climate Change, or IPCC, puts out big reports, huge, thick reports on the state of climate science, and each time there are 3 working groups, each of which produces a thick report. Working Group 1 about the physical science basis of climate change, Working Group 2 on impacts, adaptation and vulnerability to climate change, and Working Group 3 on mitigation, in other words, stopping of climate change. The topic I'm talking about figures in both the physical science basis and the impacts, and it's quite interesting to see how it has been treated. And I should say that these reports ought to be authoritative. They are produced basically by a very large cross-section of the relevant scientific community, and they are also scrutinized in incredible detail by many, many reviewers, far more than most of the scientific literature. So you'd have thought they ought to get the story right, but there is a bit of a problem here. And it's, as I mentioned, an issue that really rather urgently requires resolution, because it has considerable implications, for example, for conservation policy, which I'll come back to at the end. If you look in the most recent IPCC report series, which came out in 2014, you can find all of these, the DO events. There's a good treatment of them in the chapter about past climates. So the details are all there and perfectly correct, as I would expect, considering there were many very good scientists producing that chapter. But when it comes to the summary, you find some strange things. You find there really isn't much about rapid climate changes, and there is a figure given for the rate of change at the end of the last ice age, but the figure is given in degrees per 1,000 years. So that number is quite small, but I don't see what is the point of talking about degrees per 1,000 years for a change that happened in 20 years. So I think there's a bit of a problem in the way in which this has been kind of presented, sort of like up to the top. Then in Working Group 2, GO events, it turns out, are never mentioned. And there is some analysis of the potential vulnerability of different groups of organisms to rapid climate change, which comes to a surprising conclusion. And it's not based on the past data that I've been talking about, but it's based on completely different evidence for very recent effects of very recent climate change, which of course have been relatively small, but they are nonetheless detectable. The conclusion is that large mammals should be okay. If I slightly oversimplify, large mammals should be okay. Small mammals might have a problem. Plants that can't move, like trees, should have a big problem. So I don't know what to make of this, because it appears to be directly contradictory to the paleoecological evidence. This really needs sorting out. I would love to sort it out. because it has obvious practical implications. Conservationists have been thrown into confusion, I think, by climate change, because there is this idea that species simply will not be able to keep up with the rate of climate change, and in particular of the velocity of climate change. Velocity is used to refer to the extent to which a given climate moves across the landscape. So it's dependent not only on the rate of change in time, but also the gradient in space, and particularly over sort of flat terrain, the velocity of climate change can become extremely high. But nobody's really quantified the past velocity of climate change. And so there have been a number of papers based on velocity that basically conclude that most species have had it. And from the conservation point of view, you might conclude that in that case, the only thing that we can do to preserve species is actually to move them, to help them to colonize new habitats. Or perhaps it suggests an emphasis simply on conserving their gene banks. Obviously, simply conserving seeds of plants so that they can, in some future time, be moved to some other habitat. So this is a kind of a last-ditch rescue operation. Our interpretation of the paleo record suggests that actually that would be the wrong place to focus, that instead we should be simply focusing on removing obvious barriers to migration. Now, it's quite true the present landscape is a very different landscape from that existed at the end of the Ice Age, because we've messed around with this in many ways. We've fragmented it, we've replaced forests with fields and so on, so we've made a lot of changes, and so conservation policy might perhaps focus on what is needed to ensure continuity in the landscape, rather than sort of mounting some kind of last-ditch operation to avoid extinction.
When we think about the climate and we're thinking about the energy of the climate, it's essentially all coming from the sun. There's no other source of energy. The amount of energy coming out of the centre of the Earth is tiny. So all the energy that's forcing the climate system is coming from the sun. So when we're thinking about what causes climate change, it's quite interesting to think about how changes in the sun, or indeed the solar radiation reaching the Earth, can affect the climate. The first thing to think about is the Earth's orbit around the sun. So that is not in a circle, it's in an ellipse, and it goes further away at some times of the year and then nearer and then further away again. And of course there's more solar radiation getting to the planet when the Earth's nearer in. At the moment that's happening in about January, and the furthest away is in about July. But that varies on very, very long timescales, so like about 100,000 year timescales, that very, very slowly evolves, the eccentricity of the orbit. Another factor that is responsible for the distribution of radiation over the globe is, of course, the tilt of the Earth's axis to the plane of the orbit. And that will result in the development of seasons. So when we have the northern hemisphere tilting in towards the sun, it's northern hemisphere summer and southern hemisphere winter. And when we have the other way round, it's southern hemisphere summer and northern hemisphere winter. So we have the amount of solar radiation distribution over the globe is varying, dependent on that. That tilt of the orbit also varies on tens of thousands of year timescale. The final and the third parameter which affects the amount of radiation getting to the Earth in terms of orbital parameters is called the precession, and that's telling us at what point on this elliptical orbit the northern hemisphere is pointing in towards the sun. At the moment, the northern hemisphere is pointing in towards the sun when it's at the furthest point in the elliptical orbit. But that parameter, that timing, also varies on tens of thousands of years. So we have these three parameters that are determining the Earth's orbit around the sun, and they will influence the amount of radiation that's coming from the sun onto the Earth, and also its distribution over the Earth. So we can see, if we look back in climate history, we will see a record of the change in solar radiation in the climate. And the most obvious example of that is the existence of ice ages. If we look at how the ice ages have occurred, they occur on approximately every 100,000 years. We're fairly sure that they're due to changes in the eccentricity of the Earth's orbit around the Sun. The fact that they're not harmonic and smooth and sinusoidal as you might expect in these very slowly varying orbital changes is an interesting question, and that is almost certainly due to the release of greenhouse gases, particularly carbon dioxide, from stores in the climate system. So when the solar effect begins to warm up the climate, then that warms up stores of carbon dioxide, releases it into the atmosphere. That gives you more greenhouse effect, gives you more warming, and you get a much sharper warming than you would have had just due to the orbital variations alone. So there's a coupling here between natural carbon dioxide greenhouse effect and changes in the Sun's orbit. So that's all changes in the amount of radiation that reaches the Earth due to orbital variations. The Sun can be sitting there not changing at all, just pumping out its constant energy, and that's not having an effect on this particular variations. And I've been talking about variations on very long time scales. More important for consideration of current climate change is how changes in the Sun itself might influence the climate. So we know that the Sun's varying. You can see very clearly, don't look at the Sun, but if you did, you'd see solar flares and eruptions and bright patches, and the other obvious pattern is sunspots. And we've known about those for many hundreds of years. The ancient Chinese used to observe sunspots, so that we know that the Sun is not constant, that it's varying in time. And the question is whether any of these factors might actually influence the climate. The fact that there's black spots on the Sun, or it gives out pulses of energy or pulses of plasma, it's not obvious how they might affect the climate. People have asked this question for hundreds of years. In fact, in the 19th century, there was a big activity called sunspottery, where there was a lot of statistical analysis of the numbers of sunspots related to various meteorological parameters. The most famous of which was by William Herschel, who was a very famous scientist, very substantial scientist. He did some work on how the price of wheat on the London Stock Exchange responded to sunspot numbers. The price of wheat obviously corresponding to supply of wheat corresponding to climate. So he was trying to do that, a very interesting question. I think the statistics of his results are not very robust. Looking a bit into time progresses, if you look in about the 1930s or so, the development of radiometers could actually measure how much radiation is coming in from the Sun. So here we're trying to investigate a physical link between the energy coming in from the Sun and the surface temperature. One suggestion was that when there was more sunspots on the Sun, there would be less radiation coming from the Sun because the black spots would be blocking out some of the radiation. Perfectly plausible hypothesis. But when they were taking these radiometers up mountains. There's a guy called Abbott in the United States going to really clean areas up mountains, trying to get long records of solar radiation, trying to relate it to sunspots. He couldn't do it, and of course he couldn't do it not because there's anything wrong with his instrumentation, but really because of the atmosphere in the way just blots out quite a small signal. Since we've had satellites, of course, we've known that solar radiation does vary, and it varies in phase with the sunspot cycle and in phase in a positive correlation. So when there's more sunspots, there's more radiation coming from the Sun. When the Sun is more active, it not only produces black sunspots, well, they appear black to us, but it also produces brighter areas that we can't see with the naked eye, but can be seen in various cameras. And the brighter areas, the effect of the brighter areas dominates over the effect of the darker areas, so that there's more radiation coming out of the Sun when it's more active. So I've mentioned solar flares, which are very intermittent on very short time scales. Well, they vary on century time scales, but they also vary on a very well-known 11-year cycle. So you've heard of the sunspot cycle, and there's a certain amount of effort that goes into understanding whether the weather and climate vary with an 11-year cycle. Another indirect measure of solar activity is actually cosmic rays. So if you're looking at galactic cosmic rays, these are coming from well outside of our galaxy, but they are coming to the Earth all the time. The arrival outside the solar system is fairly constant, but when the sun is more active, its magnetic field strengthens and the cosmic rays are deviated. So there's an indirect relation, so that there's an inverse relationship between the number of cosmic rays and solar activity. So if we have a measure of what the cosmic rays were doing, we know what the sun was doing. And we have a measure of what the cosmic rays is doing in the cosmogenic isotopes, clues in the name, as they go back in the past. So we can look in all sorts of geological and Earth records of what carbon-14 or beryllium-10 was doing over history, and that gives us an idea of essentially what the solar magnetic field was doing, and that's an indirect measure of solar activity. So we have all these measures of solar activity on different time scales, but now we want to see actually whether these changes in the sun have any effect on the climate. One, can we detect any signals in climate that correspond to these changes in solar activity? Two, can we explain them? So it's a sort of statistical question and it's a physical question. In terms of statistics, I've talked about the cosmic ray records of longer term solar activity, and we can compare those with temperature records, proxy temperature records that we have of global temperature. And we can detect some small correlation. For a long time, there was the idea that the Little Ice Age, as it was called, in the late 17th century, in which the temperatures, especially in northwest Europe, were cooler, corresponded to what was called the Maunder minimum in sunspots. So that was a time when no sunspots were observed for a period of perhaps 50 years or so. We know that it wasn't just because people weren't looking, or that they weren't trying, or they weren't seeing them, because they were measuring them before that. They were trying to see them and they couldn't see them, and then they were seeing them after that. So it was actually a depletion in sunspots occurring. So there's this sort of correlation between the Little Ice Age in temperature and the Maunder minimum in sunspot activity, and it's been a sort of trope of the whole science area that these two are linked. Actually, a new idea, which is possibly going to put a spanner in the works, is that we now understand that there was a lot more volcanic eruptions around the time of the late 17th century, and in fact it's probably the fact that there was more particulates in the air from the volcanoes causing the cooling, as opposed to lesser solar activity. So actually we're getting, it's a more complicated picture than was previously understood. That being said, what about the 11-year cycle? Well, there are measures of 11-year cycle variability in a number of different climate records. The most obvious of which is up in the stratosphere, and you can see 11-year cycle in stratospheric temperature and in ozone concentrations. Nearer the surface, there are 11-year signals. It's quite difficult to extract. They're quite small and the statistics is difficult, but it does seem that there are indications, particularly in the North Atlantic region, where we seem to get colder winters when the sun is less active on the 11-year cycle. So we've got these indicators of various climate effects. Another one is Pacific Ocean temperatures in the tropics, which seem to be surprisingly cooler when the sun is more active. So if we think the statistics are correct, we now need to understand the physics of what's going on. We can understand the global temperature, surface temperature, these very, very small changes of perhaps 1 or 2 tenths of a degree in response to changes in the solar radiation, purely from radiative forcing ideas or just from energy balance ideas. But if we want to understand these more regional effects of solar activity, we need to look a bit more carefully at the physics of what's going on. One very interesting aspect is of solar variability is that although the total radiation is changing over the 11-year cycle by perhaps a few tenths of 1%, so a very small amount, actually that's not the same at all wavelengths of the solar spectrum. So that's true in the visible, where of course most of the energy in the solar spectrum is coming in, but in ultraviolet wavelengths the variation is much larger. So if you go from say 300 to 200 nanometers wavelengths, you find that there's several % variation in solar radiation over the solar cycle. And if you go to 100 nanometers, getting further away in the UV, it's doubling between solar max and solar min. So clearly this is an interesting physics question. What happens to this UV? We've got the big changes in the UV. Where is it absorbed in the atmosphere? Well, it's absorbed in the upper atmosphere. And in particular, the slightly closer UV, the 300 to 250 nanometer wavelengths, is absorbed in the stratosphere. And we can see changes in temperature in the stratosphere, we can see changes in ozone in the stratosphere, which is very interesting in its own right, but that doesn't tell us about the climate of the surface. So current work is very much focusing on coupling between the different layers of the atmosphere, the stratosphere and the lower atmosphere, the troposphere, and also coupling between the troposphere and the oceans as to how some of these apparent solar effects take place. We can now understand that changes in the stratosphere can affect the surface climate through changes in the winds and the circulations. And then there may be a knock-on effect of the wind stress on the oceans producing some of the observed ocean effects. So this is really where a lot of the current research is going on. In summary, changes in solar radiation reaching the Earth, either because of the sun's variation or because of the Earth's orbital variations, is fundamental to our understanding of climate and climate change. And we need to understand that in order to be able to be more certain about human activity and how that's affecting the climate. Very important for understanding the effect of the sun on the climate, of course, is knowing what the solar radiation is doing. And we now have satellite instruments that are flying up there, measuring the solar radiation, measuring the spectrum of solar radiation, right the way from X-ray through to the far infrared. So these measurements need to be carried out with extreme precision and also, importantly, with a stability that allows us to know whether or not the solar radiation is varying. And these satellite experiments have been in the UV for perhaps a couple of decades, but the ones that are going into the near UV and the visible have only been going since about 2003. And the technology is not quite good enough yet, but it's being developed all the time, and it's really exciting to see how the data that they will provide will give us extra information into the future. When we have these data, we can then use them in our models of atmospheric chemistry in the stratosphere, of the climate models, and see how the temperature effects affect the upper and lower atmosphere and how that couples to the oceans, potentially to the ocean circulations, and we can have a much better picture of how the sun affects the climate. So I'm going to talk about radiative forcing of climate change, and in order to understand that, we need to understand about the radiation balance of the Earth. If we consider the Earth as a planet sitting bathed in solar radiation, we can see that it's going to absorb some of the solar radiation. On average, if there's no climate change, and if we average over the globe and over a year, the amount of solar radiation absorbed, the heat of that, must equal the amount of heat radiation leaving. So there's a radiation balance between the solar radiation absorbed and the heat radiation emitted. Distributed over the globe, of course, that's quite different. It's going to be different at different parts in the globe, but let's just think of the Earth as a sort of planet sitting in space. That will vary over the year. As the Earth moves around the Sun, there will be different parts of the planet receiving different amounts of solar radiation, and of course geographically it will vary too. But we look at the planet as a whole, we see the radiation coming in equals the radiation going out. So when we talk about radiative forcing of climate change, we're going to think about a disbalance in this radiation budget. So first of all, I'll talk a little bit about what happens to the radiation inside the climate system. The sun's radiation arrives on the outside of the atmosphere, and it will penetrate the atmosphere. About half of it gets through to the surface, and heats the surface. About a third or a quarter gets scattered back to space, and the rest of it is absorbed within the atmosphere. When it heats the surface gets hot, and that emits heat radiation, and that heat radiation starts to transfer up through the atmosphere, but it is strongly absorbed by the atmosphere, and in particular by the gases that we become known to be called as greenhouse gases. The strongest greenhouse gas is water vapour. That's perfectly natural in the atmosphere, and that will absorb a significant proportion of the amount of radiation that's leaving the surface. So with all that being equal, the surface temperature of the Earth is 30 degrees warmer because there's an atmosphere there, because it's absorbing the heat radiation, it's acting like a blanket, than it would be the case if there was no atmosphere and it was just a planet sitting bathed in solar radiation. So we can see now that the radiation balance is, at different levels in the atmosphere is very important to determining the climate and determining the surface temperature on the Earth. Now, I've mentioned water vapour is the most important greenhouse gas. The second most important one is carbon dioxide, and that does about, naturally occurring carbon dioxide does about a third the amount of water vapour in terms of trapping the heat radiation. When we talk about climate change, of course, we're going to be considering how the variation in greenhouse gases will affect the surface temperature. Other factors that affect the radiation balance are the reflectivity of the planet. So I mentioned that some of the solar radiation was getting scattered back to space. That is by clouds and also by bright surfaces like ice and deserts. And also particulates in the atmosphere will reflect sunshine back to space, so any changes in those properties will also affect the climate. So when we think about climate change and radiative forcing of climate change, we're thinking about how any of these things affect the radiation balance. Now, the concept of radiative forcing is very useful because what we found by experiment and observation is that if you get something that forces a net imbalance in the radiation at the top of the atmosphere, that is linearly related to a change in surface temperature. So, for example, the global average radiation coming in and radiation going out is about 240 watts per square metre over the Earth's surface. If you change that by 4 watts per square metre, you will get a global surface temperature change of something like 2 degrees. Doesn't matter what's causing the forcing, just the magnitude will give you that result. So it's a very useful concept because it means if we can calculate the radiation change, the radiative forcing, we get a very approximate, it is approximate, but first idea of what the surface temperature response will be. So we don't have to run the very, very complicated climate models and use loads and loads of computer time to get this very, very, first idea of what the magnitude of the effect will be. So we calculate potential radiative forcing due to these different factors, and we can thereby compare their different effects. So a very obvious one would be if the sun suddenly put out more energy, that would be a positive radiative forcing. If we put more carbon dioxide or other greenhouse gases into the atmosphere, that traps the heat radiation. That's a positive radiative forcing. If we put more particulates in the atmosphere or brightened the surface somehow, you can brighten the surface by chopping down trees and making more deserts. That will be more reflection of solar radiation back to space. That's a negative radiative forcing. So we can calculate the radiative forcing due to any of these different factors, and that will give us an idea of what the climate change impact, globally averaged at the surface, will be. It doesn't give us any details, but it gives us an order of magnitude. So that's very useful when we're thinking about new gases. So, for example, you will have heard of chlorofluorocarbons because they're the gases that were implicated and indeed responsible for causing ozone depletion high in the stratosphere over the Antarctic, depleting ozone, and they have now been banned from production because of the harm that they're doing to the ozone layer. But another very important physical property of these chlorofluorocarbons is they have a very, very strong greenhouse effect, and they're very long living. So while they're not contributing much to the greenhouse effect at the moment, it is a significant amount, and it will remain there until they very, very slowly die away. So if we understand if people are going to produce different sorts of gases in the future, we can identify what their radiative forcing is, we can predict what their climate change impact might be. So looking back in the past, we can calculate radiative forcing due to natural factors and also due to human factors, and see how we think that might have affected global temperature, and then we can compare that with the temperature records and see if the radiative forcing is actually working as we have defined it. So we can look and see how we think solar radiation's varied. We can also look at volcanic eruptions. Of course, that's perfectly natural, nothing to do with human activity, but they do have a large temporary effect on climate. So if you get a big volcanic eruption, it throws a load of stuff up into the atmosphere, and that stuff gets high enough, it sits in the stratosphere, and it can stay there for, say, 2 years, reflecting sunshine back to space. And there's very clear records of temperature at the surface which show cooling in response to big volcanic eruptions. So that's perfectly natural. Then we can look at how changes in the greenhouse gases have occurred over time, in particular carbon dioxide, but also methane, nitrous oxide, ozone and the chlorofluorocarbons and other gases, how those concentrations have changed in time, and we can look at their radiative forcing values and consider how much they must have contributed to temperature change in the past. And given the uncertainties on those values and also the uncertainties on the temperature records, we find that they match fairly well. This means that if we can predict into the future what the radiative forcing of different factors is going to be, very difficult to predict volcanoes, very difficult to predict the sun, but we can have variations on those as we choose. We can have an idea of what perhaps the range of CO2 values might be, or methane, and predict the radiative forcing, and that will give us a very gross first order idea of what the global surface temperature change will be. It won't tell us what will happen in different regions of the globe. To understand that, we need to use the climate models that can predict regional variations, but it will give us a global picture. So radiative forcing is a very useful concept. I've mentioned how particulates reflect radiation back to space and cool the climate, but there's a number of other effects that they have which have a sort of knock-on effect on the climate. So for example, if you have particulates in the atmosphere, they act as condensation nuclei for clouds. So in general, if you have more particulates, you get more cloud. If you have more cloud, you have more reflection of solar radiation, and that again will have a knock-on effect on the radiative forcing and the climate change. Now, it's more complicated than that because it depends at what height in the atmosphere these particles are living as to what sort of cloud they produce and what effect that cloud has on the climate. It also depends on the size of the particulates, their chemical composition, and for example, whether they're just black like soot or white like sulfate as to what their effect on the climate will be. And there's a lot of work going on in trying to understand that. There's an even further complex addition to that problem, which is how long the clouds live. All clouds need condensation nuclei. In perfectly natural clouds will form around perhaps sea salt aerosol or dust aerosol, and that's where the clouds form in the natural climate. If you have more aerosols, for example due to human activity, you've got more condensation nuclei. You may have the same amount of water vapour, but more nuclei. So what happens is you get more, but smaller drops. The smaller drops are better at reflecting the sunshine to space, and they also are longer lived in the cloud. They're less likely to fall out as rainfall. So you can see that there's all these knock-on effects in terms of the physical properties and the longevity of the cloud, which we need to understand a bit further in order to predict how the climate might respond to these factors in future.
So one of the key aspects of understanding of how humans and climate and the Earth system interact that has become more and more important over the last 20 or 30 years has been human management or mismanagement, however you want to look at it, of the land surface. So how do we interact with vegetation? How do we manage the natural landscape and the sort of agricultural landscape for our benefit? Because that's what we do as humans. That tends to be what we do. We colonize new places and we utilize the resources that are available to us. We've always done that. That's what we're very good at. What we're not so good at is knowing when to stop and what the limits of that are and how to manage the impact of those things. That's partly because the dynamics of those things are very complicated. So one aspect where that has become very apparent over the last 30 or 40 years, or really since the advent of satellite observation, is how important forest deforestation and degradation have become. So we all know, the figures about how terrible deforestation is and how it's going on across different parts of the world. It's happening everywhere. So as an example, close to home here in the UK, we are one of the least forested areas in Western Europe. So about 12% to 14% of the UK is forest, but of that, the vast majority of it is planted coniferous woodland, so essentially commercial plantation forest that was planted mostly since the beginning of the 20th century, after the First World War, and in fact this is a little sort of bit of historical context here that just shows some of the challenges that they're facing. So the UK isn't considered to be a forested landscape at all, and it isn't. It was. So if we go back 500-600 years to pre-industrial revolution, so not that far, the majority of the landscape, particularly the lowlands in the UK, would have been covered with dense deciduous woodland. Lots of large animals, so there would have been wild boar, wolves, bears and so on. That changed dramatically as populations increased and became more mobile and deforested the landscape for timber primarily, but for firewood, timber and fuel. And then also to manage the landscape to clear for agriculture, so arable and cattle grazing. So all of these pressures on removing forest. It reached its lowest point, so the UK forest was down to a few percent cover by the end of the 19th century. And so when the First World War came along and the demands for timber were required for building trenches on the front lines of the First World War, essentially the UK ran out of timber for doing that. And so the government decided, look, we can't allow this to happen. If there's another war like this, we need to have timber to provide this. And so they established the Forestry Commission, whose job it was to make sure that the UK had enough timber, and that was by planting conifer forest. So I use this example of, the sort of almost accidental deforestation that happened and degradation of the woodlands of the UK that happened gradually, then increasingly rapidly as the population increased and urban areas got bigger, to the point where when it suits us and we realise there's not enough woodland, then we decide, oh, it's gone too far. Now we ought to do something about it. And the woodland in the UK has increased in cover quite a lot over the last, to the end of the 20th century. We're at the highest point for 500 years. But of that, very little of it is the same kind of woodland that would be recognisable 500 years ago. So in microcosm, that is a problem that's going on worldwide in terms of the encroachment into forests. So why is that important? It's important for a number of reasons. That globally, these forests store huge amounts of carbon. That carbon, if it's stored in the forest, it's not in the atmosphere. Deforestation and degradation, and I will separate those things. So deforestation is where you just cut the whole forest down and you take it out and you do whatever you're going to do with it. Most of the time you either use the higher quality timber, and then a lot of the lower quality timber either just gets left there, or it gets used, some of it gets used for fuel wood and so on. So deforestation, and then degradation is the gradual encroachment onto forested environments. So that might be due to low-level agriculture, it might be to low-level clearing for woodland and for settlement. It might be due to building roads. if you build roads through forested areas and you increasingly fragment those forests, their value and their richness in terms of species changes dramatically because of connectivity. So, you start building a network of roads. You don't actually necessarily remove a vast amount of forest cover, but if you chop it up into smaller chunks that are cut by roads, then those chunks of forest become more and more isolated from each other in terms of seed dispersal, in terms of small mammals, birds, larger animals. And that has all sorts of implications for the resilience of those forests, how their response to fire, their response to drought, their response to all kinds of other stresses that are coming their way, partly as a result of us, partly a result of changing climate, which is also as a result of us, but for all sorts of reasons. So degradation is the sort of gradual lower intensity loss of forest, which the distinction between those two things is that one of the first question we want to answer is how much are we losing? And answering that question for deforestation we do pretty well, because it's the sort of thing again that we can use satellite data to monitor, and we have done over the last 20 or 30 years. And there's been some really noticeable successes. So for example, deforestation in the Amazon was approaching a peak in the 90s. Some of it was legal, was government exploitation of forest resources that were sold off to logging companies. Most of it was illegal logging, and it was very hard to track. And if you can't track it, it's very hard to prosecute people, it's very hard to legislate. The whole process requires you to have reliable information about where it's happening and as soon as possible after it happens. And so the Brazilian government actually took a very strong lead on this and developed their own satellite monitoring program, which allowed them to say where illegal logging was happening, when it was happening. And that sort of deforestation program enabled them, there has to be the political will to do something about it, but that also requires people to see, yes, it's happening here, it's happening on my backyard, somebody's taking forest that belongs to me, that belongs to us. And so when that happened, it was a lot easier for the Brazilian government to make those kind of political things stick. And that's what they did. And so they had a notable success in the 2000s, the late 2000s, in reducing deforestation. It's the one time anywhere, particularly in tropical regions, where politicians have managed to reduce deforestation. So I would sort of say that the more recent picture is perhaps not so optimistic. There's been an upswing again, but we can use satellite data to monitor deforestation and measure it pretty well. So if people decide to do something about it, we have the tools to do that. Degradation is a lot harder to spot because often you don't see these very obvious patterns that you get with deforestation, where whole chunks of forest are disappearing. That is much less obvious when there's low-level encroachment into forest, when there's clearance for agriculture, even when there's selective logging. So if you're an illegal logging operation, the sort of most stupid thing you could do is go in and just chop down a chunk of forest because it's obvious. So the thing you do is you go in and you pick the trees that will be most commercially valuable to you, you chop those down, and then you drag them hundreds of meters out of the forest to the nearest roads. In the process, you leave a gap in the canopy, and then you leave these trails through the forest, which are hugely destructive, but actually very difficult to see from satellite data. So degradation is a harder thing to map. It's across a much wider spectrum of forests. It's not just tropical forests as well. It's temperate forests, and it's in boreal forests as well. And so degradation is known to be a big cause of loss of forest in general, of reducing the quality of those forests for their resilience to climate, their value as an ecosystem service to us, selfishly, but to all other organisms that depend on them. So there's been a lot of work, again, in trying to understand how we can map degradation rather than just purely deforestation. And there are UN-led activities in order to try and quantify those things. So the UN RED Plus, which is reducing emissions from deforestation and degradation, which recognises the fact that it's not just deforestation, it's degradation as well. And addressing those challenges will require, again, it will require political will to do something about it. But what what politicians require is hard information that says, yes, this is happening, and we all agree that the methods that we're using to monitor these things are something that we can all sign up to. And that's not necessarily an easy thing to do. But again, satellite data are helping us to build those pictures that will then enable, you know, global institutions to turn to politicians and say, if you want to do something about that, we have the tools to do that.
So I studied the biosphere as a whole, and this is a relatively new development. Most of my work concerns the land biosphere, but of course the ocean has a biosphere in it too. The study of the biosphere on a global scale is something that's relatively recent. The perspective, the new perspective that we have now only dates back to about the 1980s or so, when it had finally become clear that human activities were massively modifying ecosystems, and not just ecosystems, but indeed the composition of the atmosphere, and that the two things were interrelated. So in the late 19th century, a Swedish chemist called Svante Arrhenius theorized that industrial activities involving fossil fuel burning must be putting carbon dioxide into the atmosphere and increasing its concentration. And he also theorized that this should be leading to global warming, and he even made a calculation about how large it would be, and the calculation is fairly close actually to modern calculations of this effect. But it couldn't be tested because there was no instrument that could measure CO2 concentration accurately enough to find out whether it was increasing or not. And that actually had to wait until the 1950s when Keeling invented a machine that could measure CO2 with high precision, and as soon as it had been set up for a couple of years, it had become very clear that CO2 was increasing. And of course it's been continuing to do so ever since. So we had to wait half a century for confirmation of Arrhenius' ideas about CO2. We had to wait even longer for confirmation of his ideas about global warming, because climate is of course a very complex thing. Climate is not just changing uniformly from year to year. Climate, we know, is warming, but the signal, if we look back over the record, the signal is not really clear until about the 1980s. It's only about then that the signal appears from the noise. So now we know that Arrhenius was right, but a lot of other changes in our way of looking at the biosphere came with this, because of course CO2 is fundamental to plant life. So plants depend on CO2, they take it up, and decomposing microbes put it back, and the flux involved is enormous. So large, in fact, that any perturbation to that flow of carbon dioxide into ecosystems and back out again, any small perturbation would be of a similar magnitude to the amount that we're releasing by fossil fuel burning. So it has gradually become clear that there is an intense interaction between the biosphere and the atmosphere, and that there is something which we now call the global carbon cycle, which is the exchange of CO2 between the atmosphere and the ocean, and between the atmosphere and the land, and that basically it is all one system. So with this new understanding of the biosphere, there was a considerable pressure to develop global models of how ecosystems work, and how climate modifies ecosystems, how climate controls ecosystems, and how ecosystems then in turn influence the carbon cycle. It was also gradually becoming clear that ecosystems would have more direct effects on climate, because most of the water that comes into the atmosphere over the land surfaces is actually coming through plants. And so any change in the nature of the vegetation cover can influence the water exchanges, and it can also influence other physical properties like the heat absorption. And so we had a new notion of the biosphere as a highly interactive component of the Earth system. What we didn't have was really the science required to develop numerical models. We had a science of ecology, but it was all about small-scale processes, much more about trophic interactions, much more about species than about physical processes and physical exchanges. So the theory had to develop pretty quickly. So we have Earth system models, which are climate models basically, but which are originally derived from weather forecasting models, but adapted to a longer time perspective. But these models now actually incorporate models of the biosphere. So that seems like quite an achievement, but there are a few problems. And one of the problems is that when they're asked to make projections into the future under various scenarios, they all give different answers. And I guess they can't all be right. There are also quite large biases. And so there's a lot of work that needs to be done, and the models are getting more and more complex at the moment, but they're not really actually getting better. And so what has now been realized by many scientists in the field is that we do need to do better. In a way, we did this in too much of a hurry with hindsight. So models have been developed independently by different groups without much cross-checking, without enough comparisons with data. Data here are a key issue, because when we first started to work on these models, there were very few data of the large-scale kind that we would need to test all of our assumptions. The situation now has changed radically and is very much for the better. So not only do we have the highly precise measurements of carbon dioxide and other constituents of the atmosphere, but also we have measurements, local scale measurements of the flux of CO2 and energy between ecosystems and the atmosphere at several hundred sites across the world. And we have physiological measurements at the plant level, which is of course small scale, but it becomes large scale when you have thousands of measurements made by different groups that have been compiled into databases. And then finally, we have the tremendous resource of data from satellites, which are now of course just those that are continuing, are just giving us longer and longer records, but also records that are getting more precise and have more and more properties of the land surface, such as its greenness, which is obviously fundamental, because the green colour is chlorophyll, and that's what does photosynthesis, that's what takes up CO2. And also other properties such as the reflectivity of the land surface, and even now indicators of important quantities such as the light use efficiency of photosynthesis, remarkably, can actually be measured from space.
Okay, so today I'd like to talk about climate change in human history and the interactions between them in the past. And so sort of clearly, if you go back far enough, back 50 million years or so, then there's no humans, and it's just after the dinosaurs have died out, and it's a wonderfully warm world where there's crocodiles living in the Arctic. And since then, the world cools, and it gradually cools, and at some point, about 30 million years ago, you get ice sheets on Antarctica, and then slowly it cools more until you get to something about 5 million years ago, and then you start having things that we regard as our ancestors, and so you have human ancestors, and that's in a period called the Pliocene, which I like to study sort of 5 to 3 million years ago. And the Pliocene was still a warm world. It was a couple of degrees warmer than it is today, but it had carbon dioxide levels of about 400 parts per million, which is what I'm breathing today. And so there was this warm world, and there were our ancestors in it. And then over the course of this sort of long cooling that the world's experiencing, you start crossing a threshold about 2.8 million years ago, and the world starts going into glacial interglacial cycles is a technical term, or ice ages is probably more common, but where you start getting really big expanses of ice covering, say, North America and parts of Eurasia. And these big expanses of ice absorb hundreds of meters of water. And so the ocean drops by 100 meters. But there's a sawtooth pattern to this. And so it's cold for about 90,000 years, and then it suddenly gets warm again for 10,000 years. And sort of that pattern goes through. And then sometimes, and then sometime about 2 million years ago, you start seeing changes in the tropical circulation. And those changes impact the climate of Africa, and quite whether it's that the climate of Africa becomes drier, or whether it's that the climate of Africa becomes more variable and the lake levels start changing, we're not really sure. But something in that climate change leads to a sort of development and evolution of our ancestors into something that we recognise as Homo, so the human family, and then sort of you get those ancestors are in Africa for quite some time, and then they slowly spread out over the last 100,000 years or so, across Eurasia. Anatomically modern humans coming in, and then there's a period of stable climate, and so that stable climate sits for about 10,000 years. And so what had happened was you have the real depth of the last ice age was about 20,000 years ago, and there were the ice was at its greatest extent, and then it starts melting and it starts decaying away, and the sea level starts rising, and as that happens, the world's gradually warming up, and so the depth of the last ice age, you're looking at a world about 4 degrees colder, and the carbon dioxide level was about 100 parts per million below its sort of background, the pre-industrial level, but then the carbon dioxide level starts rising, the ice sheet starts falling away, and this is all driven by changes in the Earth's orbit. There's no human influence in it at all, but you start seeing that, and then after about 10,000 years, the majority of the ice is all completely away, and you get left with a very stable climate that persists for about 10,000 years, and it changes slightly, but it's generally a flat and nice and stable climate. And within that stable climate of this period called the Holocene, you start to see real innovations taking off in human culture. And so about 9,000 years ago, you see the first aspects of domestication, where over in the Fertile Crescent you're getting crops, and then that domestication occurs independently elsewhere. So in China about 6,000 or 7,000 years ago, and then New Guinea about 4,000 years ago, and over in the Americas as well, somewhere between sort of 5,000-6,000 years ago. And so you're getting this convergence of human culture into farming, and sort of moving from hunter-gatherers into farming. And that then pulls through to changes in the way that we live. And once you have a farming civilization and you're sedentary, then it's clearly worth putting more effort into where you live. And you might also be making a surplus, and so you can afford to use that extra food to supply a higher sort of civilization, I suppose, and you see the births of these first civilizations. And interestingly, one of the very most famous ones, the Egyptian civilization, is actually thought to be slightly influenced by the climate getting worse. And so about somewhere between 14,000 years ago and 6,000 years ago, the Earth's orbit was such that there were large bands of rain in northern Africa were moving really quite far north, and you end up with a period that's referred to as the Green Sahara. And it doesn't necessarily mean that the whole thing's covered with grass, but it's certainly a lot greener than it is today. And in that Green Sahara, there were peoples living, and about 6,000 years ago, you start getting the first pastoralists, and so that's cattle herders, and those pastoralists were able to stick around despite the climate getting worse, because the orbit was changing very slowly back, and so it was turning into the dry Sahara we know. But it didn't turn quite as fast as it perhaps should have, because those cattle herders were able to sort of support the climate through moving nutrients around and helping the vegetation. But at some point, it just becomes even too much for them, and they have to retreat from the Sahara. And if you're in northern Africa, in the desert region, where you want to retreat to is you want to retreat to the area that has water available, which is the Nile, and so they collect on. So you sort of see an inward migration onto the Nile Valley, and with that greater population density, there's more requirement for social structure, and you start getting into the Egyptian civilization. And so sort of the climate, and it's generally stable, but with these slight worsenings and slight betterings that cause technological innovation. And that technological innovation, in a cultural sense at least, is what's spurring civilization onwards. So you have this technological innovation, and then there are cycles of this. As the climate just naturally gets a little bit warmer or a little bit colder, or maybe it's just the northern hemisphere, but we don't necessarily know. And so you have a Roman warm period, and it was warm whilst the Roman Empire spread over, and there was technological innovation associated with that, and clearly cultural innovation. Not all of it being pleasant, of course, but stuff's moving onwards. And then it gets colder going into the what we call as dark ages here in Europe. And then as the climate gets warmer again into the medieval period, you start seeing this blossoming again of culture. And then the last sort of move in the historical climate is referred to as the Little Ice Age. And so this was the period, say, from about 1450 through to 1850, where it's noticeably colder. And partly that's natural, well, predominantly that's natural, where you're getting slightly less sunspots, and so sunspots alter the amount of energy that reaches the Earth's surface, and therefore if you have less energy it gets colder. And the other thing that changes the amount of energy reaching the Earth's surface is big volcanoes. You have a big volcanic eruption, it puts lots of dust up in the atmosphere, and that stops the sun's energy coming through and leads to a slightly colder world. And if you have a lot of volcanoes going off in general, then that can lead to a cooling. And then in 1492, Columbus and his fleet set off out across the Atlantic and discovered the New World, or the Americas. And as he went, he very kindly brought things like Christianity, but also slavery and subjugation and diseases like smallpox. And that really killed the indigenous population. And the indigenous population went from about 60 million people to about 6 million people in the course of 100 years. And as they died off, they weren't farming, and the trees reclaimed their land. And slowly, as the trees reclaim their land, they're also sucking carbon dioxide out of the atmosphere. And that carbon dioxide, as it sucks out the atmosphere, leads to a slight cooling. And so you have this natural little ice age where the sun's not shining as much as it could do, and there are some volcanoes going off. And these are really small background things, but yet have a big impact on the climate system. And then on top of that, there's this what in today's context is a small drawdown of CO2 coming from the reforestation. And that leads to a slight cooling. And then from about the 1850s or so, then you really start seeing the impact of the industrialization and the increase of fossil fuel burning that leads to a much greater level of carbon dioxide reaching the atmosphere, and that's leading to the global warming that we're seeing going through to today and will continue over the course of the next 100 years or so. As we move into the future, at some point humans will stop emitting more carbon dioxide into the atmosphere, and it will balance out, whether of our own free will, that's what I hope, but it might be just that climate gets so bad that society collapses and the population collapses, and so it sort of acts as a natural brake on the amount of emissions. I don't want that to happen, but at some time the carbon emissions will level off, and then it'll take about 100, 200 years for the atmosphere to equilibrate, so to reach the level associated with that atmosphere, with those carbon dioxide emissions, and then another few thousand years for the sea level rise to really finally kick in as the ice sheets are slowly melting away. But that carbon pulse through our industrialization will level off, and then over tens of thousands of years, then the natural geological cycles should start coming into play and drawing down that carbon dioxide. And whether we then go into an ice age and it draws it down that quickly, and so maybe 100,000 years of perturbation through the human influence on the climate, or whether it's that we've put so much in there that the world has found a new stable state back like the Pliocene, so 4 or 5 million years ago, and that level stays and so sort of it stays at that level until there's a very, very gradual drawdown, and we have to go through the whole cycle of ice ages again. I'm not sure, but there was a time when the climate was naturally varying and impacting humans, and now we've crossed into the point where the climate is being driven by humans, and at some point on geological timescales we will return to a setting where the natural processes in the Earth system change the climate again.